Hello, everyone, and welcome to the second to last lecture of Inorganic, in which we're going to cover the electronic transitions of metal complexes. So, how are we going to do that? We're going to go through the key aspects of the electronic transitions, then electronic transitions focused on what's the effect on the metal, and the charge transfer transitions, in which we're actually going to contribute something more to the transition than just the metal. And this should be 3 different videos. So let's kickstart everything with the key aspects of the electronic transitions. So what are the features and how do we need to systematize them? So from the previous lectures of the same course, we organized our ideas on what holds a complex together and how do we know the structure. So now we know what the metal is doing, what the ligand is doing, and how do we figure out that the spatial arrangement is actually this and not something else. So what we used last time to actually go through the experimental structure of deductions were vibrational levels. So the vibrational spectroscopies that probe the transitions from ground state and ground level of vibration to higher levels of vibrational states. The reason we used them was because the occurrence of these vibrations is a symmetry-driven effect. You cannot activate a vibration if the structure doesn't allow it. So the presence or absence of some of these transitions is actually a signature of certain spatial arrangement of your complexes, which means you can derive your structural arrangement based on the spectroscopic features, either using infrared or using Raman. They're all probing this effect of you can activate a vibrational level. Obviously, other spectroscopies exist. These ones are key for their level of fundamental probing of your structure, the way they interact on such a fundamental sub-vibrational level of the ground state. The inevitable question that follows from this is, can we probe something more than the ground state? So if enough energy is provided to the system, you can actually change the electron distribution that you established by establishing your bonds. Now, this is an electronic transition. So if you transition the states of the electrons, you are going to change your state. So you're not going to be in the ground state, you're going to be in a different state of the molecule because you changed the electronic arrangement. A different state of the molecule will come with a new set of vibrational arrangement, inevitably. So we are not here anymore. We're not in the ground state. We are going towards an excited state. So a different solution of the Schrödinger equation, conceptually speaking. You can go there if the energy is high enough, but to go in a state that has a different distributions of the electron, you need to be in the order of several electron volts. So the type of energy you're providing is completely different. But if we look at the threshold energies, several electron volts, so more or less 100 kilojoules per mole or something like that, brings you squarely into the visible and ultraviolet range. Whereas the type of energy that we were using to probe the vibrational states, so to stay in the ground state and just make a molecule vibrate, were in the infrared region. So what does it mean to change electronic distribution, to transition into a higher state? It means that we are effectively moving the electrons from their normal configuration, so the ground state configuration most stable in the current conditions, into an excited state that is using different orbitals. So we're moving from one orbital into another. We are forcing an electron to transition beyond those HOMO-LUMO level that we arranged on the basis of you want to occupy all the lowest energy levels and then maybe go higher. At this point, we are forcing the transition, so we can go higher because we are providing the system with the necessary energy to actually go there. So a question that we had floating around in the last weeks and became more and more pressing was the idea of how do we know the value of delta? We managed to arrange all of our crystal field. We expanded the crystal field to actually account for the molecular orbital diagrams. How do I know the delta? How do I know that this energy is bigger than this energy, that this gap is bigger than this gap? Because we have a lot of different possible gaps. So whereas octahedral and tetrahedral only have one gap, the thing that we established in trying to figure out why will something want to be square planar or bipyramidal or something like that, is that you have additional gaps in energy. So, and which gap becomes the relevant one is your key fundamental question to ask yourself, is this the new most stable arrangement of your molecule? But the frontier orbital are the one at ground state. So the question of how big is your gap must be proven and probed experimentally. So there is no way to know it until either you calculate it all from first principle or you get your first principle and you bring it through with an actual experimental feature. So provided that the transition obeys selection rules, you're able to move from a ground state to a more excited state. Why is this impactful? Is it just because we want to figure out crystal field gaps? This transition between the frontier orbitals is one of the most massive and impactful options that you have from your metal complexes. So the thing that makes inorganic chemistry famous and the things that might actually have driven you into, can I look at inorganic chemistry, is that we have things that are colored. They're nice and colored. The reason for the colors are exactly this electronic transition. So this vague concept of you have a gap in your crystal field, you have a gap between your frontier orbital is incredibly impactful to the point of the microscopic properties. And inevitably, when we say we have a lot of pretty colors, we also mean we have a lot of different shades of pretty colors. So at parity of the type of metal that you're using, so if you're using copper, you can have a bunch of shades of copper, all the way from basically black to very light green to stuff like this. Same with cobalt. The cobalt is famous for changing colors all the way through. So you can have it in green, in blue, in red, in purple. Why would you have so many options? Inevitably, you must be probing and poking at different energy levels at the frontier. So you're not using vibrational, you're actually transitioning electrons. Now, to understand how this thing correlates, so the transitioning of electrons correlating to the color, we need to remember the color wheel. So everything that you see from your actual macroscopic, my stuff is colored, is everything that the complex or the compound is not absorbing. So you are using all of the possible energy to trigger this transition. Once you have triggered this transition, all the leftover is left for you to see. So this is not an effect of the compound is shining a color at you. That would be an emission. You're looking at an absorption, and everything that is not absorbed is reflected. So every time you see something absorbing, it means that you're seeing the opposite color. So if something is absorbing in blue, it will be evident for you because it will be orange. You don't expect something to absorb in the blue and look blue in the concept of we're doing electronic transitions between the frontier orbital. So we're always seeing the opposite color. And this allows us to benchmark immediately what threshold of energies are we using. Addendum to this thing is that if every energy in the visible range is absorbed, you're looking at something that is black because there is no color left for you, but everything is getting absorbed by the substance. Counterpoint, if something looks white, is because there is no visible light absorbed, so all of the colors are coming back a U, giving you something white. So this already gives us a bit of a benchmark of what type of energies are we looking at, but then it is just a concept of give me enough energy and I will do the transition. This brings us into the idea of selection rules in electronic transitions. So we had selection rules for vibrational levels. These ones are selection rules for electronic transitions. The vibrations are not bound to this rule, but the electronic transitions are not bound to vibrational rules. So all of that symmetry analysis you did last time can bring you a long way for vibrational transitions. It can do nothing for the electronic transitions. So what do you need to obey if you're trying to transition an electron from one state into another? You want to move from one orbital and go to the next. First key rule is the spin selection rule. So if you are transitioning your electron with its spin, you are not supposed to change the number of unpaired electrons. So the total spin of the system should not change. So this delta S should remain 0. This means you cannot flip the spin if you want to transition to another level. So if you started in this way, so you had one up and one down, if you go to the excited state, you are supposed to keep one up and one down. So if this was your singlet, because you had both the electrons pair, the excited state must remain a singlet. The option that you might conceptualize of, oh, well, I will put it up, but I will put it up with a different spin, so it will bring the spin parallel, which will make the spin of the system 1 in this case, is not allowed because this will be a triplet state, and it can be conceptualized, but it is not allowed from the selection rules. So obviously these states conceptually exist. So you can have an energy state in which the spin is flipped, but they are not immediately available from, by the transition. You cannot transition to that state immediately. If you started from a singlet, you must remain in a singlet, which means you have a sequence of possible energy, but all of these excited states are all singlet state if you were starting from a singlet ground state. So you must look only here. To end up from a singlet into a triplet, you need to then cross over from the excited state. We are not going to go into that. There is some part of advanced physical chemistry that go into the photochemistry, but the intersystem crossing is the only thing that can lead you into a triplet state. Anything else will be forbidden. The second very important selection rule is that is called the Laporte selection rule. So upon the transition, you need to change the orbital. So you cannot stay in the same orbital momentum state. So you need to change the L number of your thing. Plus and minus 1. You need to move somewhere else. So if you have your S, P, D, F, whatever, move to another L, and then we can transition. So if you move from an S to a P orbital, you're fine. If you want to stay in the P, it's not fine. Addendum to this point, if you have a molecule that is centrosymmetric, the only allowed transitions are the ones that change the parity. So when we labeled our orbitals, we had all this thing of how is this orbital arranged in terms of the center of inversion. Is it symmetric across the center of inversion or anti-symmetric across the center of inversion? That's a feature of the orbital you need to consider. So if you stay symmetric to the center of inversion, this transition is not allowed. If you move from a U, which is anti-symmetric, to a G that is symmetric through the center of inversion, the transition will be allowed. Why do we have these weird selection rules? Oh, would you want to check the orbital momentum quantum number? You want to check the spins? You want to check the parity of your wave function? This is all because we are bound to selection rules. the whole universe is bound to laws of conservation. So what the selection rule is trying to do for you is systematize the conservation of the orbital momentum. So this thing will have a momentum. You're trying to move an electron that by itself will have an angular momentum. You must preserve the angular momentum. So this is a fundamental law of physics, but you're seeing here the massive impact that a fundamental law of physics, like the conservation of energy, in this case placed on the angular momentum, has. You can move or not move an electron depending on, are you preserving this quantity or not? This is a symmetry effect, as you would have noticed. So what happens if you follow the rules? If you follow all the rules, then your transitions is allowed. If you follow some of the rules, your transition is partially allowed. And if you follow none of the rules, so you break the spin, you bring the Laporte, you're moving from U to U, is forbidden. This transition will be called forbidden. Consider obviously that as you go through, every new excited state will have the vibrational substate, will have the rotational substate. Some of these things can help you trick the system a bit. We're going to go into that in a bit. How much light do you absorb the moment you do this? Well, you can use the Beer-Lambert law, which is this one. So the absorption of your substance is proportional to an inherent quantity of the substance, the concentration, and the path length of light as it's shining through. If you keep the concentration steady across different substances, and the path length that you are considering is always constant, then you can consider that the amount of absorption of your system is equal to the epsilon, which is the molar absorption coefficient, which is a fundamental quantity of the material. It is a fundamental quantity of the material because it's trying to quantify exactly this effect. How are you able to jump to higher level? Are you happy with it or not? This means that a transition that showcases itself with an incredibly large epsilon is an allowed transition. You are following all of the rules, so the statistical probability of the transition happening is incredibly high. It will always go. If you have a small epsilon, then you're looking at a partially allowed transition. It could happen, is slightly statistically challenged because some rules are broken, so often this will not be able to go through. If you're looking at something with a very small epsilon, then you're looking at the forbidden transition, which is basically happening as a statistical glitch of the system. You're not supposed to see it, you still see it. We're going to go through some examples, so then it will make more sense to see when something is fine and when something is not fine. So overall, what are you tracking in a spectrum? You will get a certain distribution of absorption as a function of the wavelength. So you give the light, how does your system react to the light? This will come with a certain peak intensity, so a peak of a certain absorption that we just clarified is directly, immediately proportional to epsilon. So it depends on the substance, on the point of view of how much is the substance happy for this transition to go through according to the selection rules. The number of peaks depends on the electron configurations. So how many electrons do you actually have to go from the HOMO up? And the number of possible jumps. So how many available excited states do you have within reach of this energy range that you are providing to the system? So how many peaks, how high are the peaks? Then the other thing is, where is the peak? So what is the wavelength in which you actually see this maximum of absorption? So this wavelength depends on the entity of the jump. So depending on how much energy do you need to give to the system to be able to go from ground state to excited state, then the wavelength is rising or dropping, depending on if you have higher energy, then the wavelength is always lower. If you need smaller energy to be able to bridge this gap, then the wavelength is higher. So this thing, this jump in energy, this where is the wavelength, is the actual factor that is going to be equal to your crystal field splitting parameter, if you really want to go in the approximate version, or the frontier of your HOMO-LUMO in molecular orbital diagram description. So with this covered, in the next step, we're going to go through some examples in which we only cover this whole business of the crossing over of the electrons from the point of view of the metal.